Hi, thanks for the introduction and for the opportunity to speak here. I'm Francesca Randone and I'm a PhD student in computer science at IMT Lucca. And today I'm going to present a paper co-written with my advisor, Mirko Tribastone, and my co-advisor, Luca Bortolussi. And this paper addresses the problem of refining a deterministic approximation of stochastic networks through a method called dynamic boundary projection. Brief disclaimer, even though my background is in mathematics, my PhD is in computer science, and the community we were trying to address with this paper was mainly the computer science community. So you can see a slightly different formalism from the usual one for chemical reaction networks, different rate functions, but I will try to draw parallels as often as possible, and I hope to be as clear as possible. Let me start with a motivating example. Here I've chosen an heterodimerization example in which we have two molecules, X1 and X2, and they are produced in bursts of m units. These two molecules can bind together and producing a third molecule, X3, and all three molecules can degrade. And if we try to approximate the average dynamics of this system with a deterministic approximation, you will find the blue lines, which are insensitive to the number of units produced each time the first two reactions fire. While if you simulate these systems, the simulated average dynamics of the system will give you the red line, which changes as the parameter m changes. And as you can see, there's a significant discrepancy in the two dynamics. So we were trying to tackle this problem, and we proposed a method in which you have a parameter n. And when n is set to 0, you recover your classic deterministic approximation. But as you increase the value of n, the solution of our method will converge closer and closer to the true dynamics of the system. So you see here that for n equals 30, you get the gray lines, and for n equals 50, you get the black line, which is in the case m equals 5, it's practically identical to the true dynamics of the system. As I mentioned before, we were addressing mainly the computer science community. Therefore, we derived this method not directly in the formalism of a chemical reaction network, but in the framework of Markov population processes. However, I mean, the underlying model is the same one. We're still talking about continuous time Markov chain, of course. And another important difference is the fact that we're not thinking about mass action kinetics. So I will repeat this, but please keep it in mind. And anyway, our method can be applied straightforwardly also to chemical reaction networks, and I will show you how. But the derivation is for Markov population processes. Okay, so this is, let's say, the general problem. Now, let's recap briefly where we are coming from. So when I talk about a Markov population process, I'm thinking about a process described by a state vector, and my state vector has m components, where m is the usual number of species. And each component of my state vector tells me how many units of a species are present in the system at time t. Then we consider a set of transition vectors, where a transition vector takes value in the relative numbers. And a transition vector is basically the difference between the vector of product and the vector of reactant that we have in a reaction for a chemical reaction network. And finally, we have that our system performs transition from state X to state X plus L, where L is a transition vector, with a certain rate which is defined by a state-dependent function f of L. And as I said before, in general, we are not considering mass action rate functions, but in computer science, it's pretty common to have non-differentiable function or rational functions, functions depending on minimum and so on. And here you can see a simple representation of a two-dimensional birth-death process evolving on a two-dimensional state space. And you can see the birth-death process formalized as a Markov population processes, so in terms of transitions and transition vector and rate function, and as a stochastic reaction networks. When the stochastic reaction network is interpreted in a stochastic way, they're exactly the same model. As we all know, to describe exactly the dynamics of such a system, we would need to derive the chemical master equation. This is a set of ODE in which we have an ODE for each state of the system. And this makes this equation in generally quite difficult to solve, quite expensive, because the state space can it is really large, usually is subject to exponential growth. So in general, the chemical master equation is quite difficult to deal with. So often we resort to deterministic approximation of the average dynamics. And these are obtained by deriving the drift function and by solving an ODE system having the drift as vectorial field. Now, when I'm talking about the deterministic approximation, I'm not talking about the normalized process, which is common in biology, for example. For me, the deterministic approximation approximates the average number of agents present in the system, not the average concentrations. And we do this because often we work with systems that do not satisfy the density dependence assumption. So keep in mind this little difference in the rest of the talk. Okay. As I've shown you before, these two things sometimes don't agree because the true dynamics of the system described by the chemical master equation can exhibit a significant discrepancy with respect to the deterministic approximation. And this is where our method comes in. In a very general way, our method tries to couple together these two approaches. Basically, we consider a truncated version of the master equation. So we write a master equation for a subset of states. And then we use a deterministic function to shift this truncated master equation across the state space. So here in the GIF, you can imagine that you have written the master equation for the states in the blue area. And then a deterministic function moves around the blue area following your process. And basically, if you collapse your blue area to a single state, you would recover the deterministic equations. While if you let the sides of your window tend to infinity, you would recover the original master equation and therefore the exact dynamic of the system. This is the main idea. The derivation, of course, is not so easy, it's a bit technical, but I'll try to be as clear as possible. Okay, to derive the equations, first we need to define what a truncation is. And for us, a truncation will be just an hyperrectangular subset of states. And our hyperrectangle is defined by two parameters, n, that gives us the sides of the hyperrectangle, and y, that gives us the position. By convention, the position will be the vertex of the hyperrectangle with minimal component. So for example, in this two-dimensional state space, the blue area is the truncation indexed by n22 and y00, because the bottom left vertex is the state 0, 0. Once you define what a truncation is, you can define a joint process xy, where x is your original process, the process you want to approximate, and y is a process that keeps track of the truncation in which x is at time t. So imagine that x is in state 1, 2, then our y will be in state 0, 0, because state 1, 2 belongs to truncation 0, 0. What happens if x transitions to another state outside the truncation? So for example, if it transitions to 1, 3, well, we will update the state of x, which now becomes 1, 3, and also the state of y, which now becomes 0, 1, because state 1, 3 belongs to truncation 0, 1. Now, of course, one state can belong to more than one truncation, but let's say that one can take care of this by suitably define a function that always identifies the right truncation, let's say, or at least one of the truncation. It's just a convention we define. So, okay, we have this joint process where x is the original one and y just keeps track of the truncation. And we can write the average dynamics of x in terms of probabilities of the joint process. And after some manipulation, you will get this expression. This expression is particularly interesting because you have two summation. The internal summation only depends on the state inside a truncation and is exactly the average computed on the states inside a truncation. And this is the part that we want to approximate with a truncated master equation. The outer summation instead only depends on the coordinates of the truncation. And this is what we want to approximate with a deterministic function that tells us which is the truncation most probable at time t. So let's start by approximating the inner summation. Here we are dealing with a truncated master equation, and our choice to derive this truncated master equation was to use an augmented truncation approximation. These are just approximations in which you consider a truncation, and whenever a transition goes outside the truncation, you redirect it to a state inside the truncation. So for example, suppose you have transition going from x to x prime, so from 3, 2 to 4, 3. In this case, 4, 3 is outside the blue area, so we redirect the transition to x star, and which is inside the blue area. And how do we choose x star? We just choose the state which is closest to the true target state x1. And basically what we are doing is to project the true target state x prime on the boundary of our truncation. And this is why we call this boundary projection. Once you do this for all the transitions outgoing the truncation, you can write a master equation for the states in the blue area. And you will get an equation like this, which in general will depend on both x and y. But with a very simple trick, you can make it dependent only on y, because you can shift from global coordinates of the states to local coordinates. And by this, I mean that my x, 3, 2, can be written as the sum of y, the truncation is belonging to, which in this case is 1, 1, and another state x0, which in this case will be 2, 1, which is the corresponding state belonging to the truncation indexed by 0, 0. So basically all my states in the blue area can be written as y plus a state in the truncation indexed by 0, 0. And in this way, we remove the dependence on x. And our truncated master equation only depends on y. this is very suitable for our purpose because once we have our deterministic approximation of y, we can just plug it in there and we have our dynamic boundary projection. But before doing this, we need to give a meaning to these probabilities we get here. And we interpret the probability of the probabilities of the truncated master equation for a certain truncation indexed by y as the probability of x, of being in state x, given truncation y, so as the conditional probabilities. And these were the probabilities that we had found in the inner summation. So we can just plug our approximation in the inner summation, and we have something, let's say, close to what we were trying to get. Now we need to approximate y. And this again is a bit technical, because first we need to derive the equations for the probability of being in a truncation y. And to do this, we need to define some transition vectors that tells us how y changes whenever a reaction takes place, but this is just notation, let's say. And once we do this, we have that this master equation for y depends on these conditional probabilities here. But for these conditional probabilities, we have just found an approximation. So we plug our approximation, which is given by the solution of the truncated master equation. And once we do this, our equation, the resulting equation for y, can be seen as a master equation for a process. And actually, this is a process for which the rate functions are time dependent because they depend on these probabilities, but is a perfectly fine Markov population process for which we can derive deterministic equation. And this is what we do. We write the deterministic equation for y, and we get this system of equations depending on the approximated probabilities. Okay, in the end, after all these passages, we're left with a system of ODE in which you have two families, let's say, of ODEs. One is the truncated master equation that gives us some approximated probability. And infinitesimal generator of this truncated master equation depends on a deterministic function y, which is obtained from the other family of ODEs, which is just a deterministic approximation of some process, whose rate function, in turn, depends on the approximated probability. So in this way, you get these two families of equations are coupled and both nonlinear. And then you have your average dynamics of the system, which can be expressed as the sum of the average computed on the truncation, on the truncated master equation, plus a deterministic function that shifts around this mean. Okay. On this method, we give some theoretical guarantees. The first one is that it is actually a refinement of deterministic equations. And by this, I mean that if you take n equals 0, you get your deterministic equations, the one you're used to. While if you set n equal to infinity, you recover the master equation for the original process you wanted to approximate. Our second result is a limit result. And we say that under mild condition of the drift, and this means mild condition on the rate functions, of course, we guarantee that the solution of our method tends to the solution of the master equation as n tends to infinity. And the mild condition are a Lipschitz condition, which we all know is very natural. The second one is boundedness, which may not seem very natural if you want to work with mass action kinetics, but as I was saying before, the systems we were thinking about all satisfied this second assumption, so it was quite natural to use it. However, I think the theorem can be adapted to the unbounded case, and I am trying to fix the details to make the proof work. Actually, let me say also a few words about how this is proved, because I think it's interesting. Basically, here we're working with a nonlinear system, and all the equations are coupled. So what we do is first we linearize the system, setting the y equals to 0, and we prove convergence of the linearized system using a proof similar to the one used for finite state projection. And then we express the full system as the sum of a linearized version and nonlinear perturbation, and we prove that in bounded interval the nonlinear perturbation tends to 0. This proof doesn't work for steady state since we are assuming bounded interval, but this is another thing we would like to extend, even though I have much less ideas on how to do this. Okay. This is, let me show you some numerical results. Actually, this is the heterodimerization model I've shown you before. So instead, I will show you this. This is Schlegel model. And Schlegel model is very interesting because for some choices of the parameters, at steady state, it exhibits B-stability. And when you try to approximate its dynamics with a deterministic system, what happens is that the deterministic system will tend to only one of the two equilibria, depending on the initial condition. If instead you simulate this model, your average dynamics will take into account both trajectories converging to one equilibrium and to the other. So again, you see here the discrepancy between the blue and the red line. What happens when we apply our method is that as you increase the n parameter, the result of our method will progressively shift away from the deterministic approximation and will converge to the true dynamics, even though it does that in a non-monotonical way. And what we're thinking about now is to tailor our approach for multi-stable system, because our idea is that instead of using just one truncation, you can use more than one, and each one can keep track of a particular area of the state space in which an equilibria is set. Okay. While I was talking, I mentioned some of the extensions we would like to work on. Actually, we also published another paper in which we try to make the method more scalable by using a rescaling of the process. However, we found that this rescaling is really model dependent and is not always the best choice to reduce the number of equations. Another thing we would like to do is to find suitable error bounds or convergence rate depending on n, because right now we only have the convergence guarantee, but no way to quantify the distance between our solution and the true dynamics of the system. This is all from me. If you have questions, feel free to ask, or even at the end when we're going to have the breakout session. I refer you to our paper, Refining Mean Field Approximations by Dynamic State Truncation, for more details. And thank you for the attention.